All right, next I'd like to take a look at how these kinds of high and low pressure regions influence the weather on a larger distance scale. And so we have this basic idea that in the areas of high pressure, we have downward moving wind. And in areas of low pressure, we have a very strong updraft. This, again, is associated with instability. If we see a low pressure on a pressure map, we know that this may be an area of storms, but at least it probably has a lot of clouds. This will be an area, if it's not in the polar region, that's probably a warm high that is associated with higher pressure air that is moving down. Now, as we go to higher elevation, what we see is that the wind patterns are a little different than they are at lower elevation. And these wind patterns are associated with the cyclonic motions that we talked about in an earlier lecture that are associated with high pressure regions tending to have winds which travel around them in a clockwise direction in the northern hemisphere, and low pressure winds tending to move in a counterclockwise direction around the low. Now, we actually have two things going on here at once. One is that the air naturally just wants to go from high to low. But while that's happening, we also have this Coriolis effect, so that near the surface, the high pressure air doesn't just move out like this, but starts to curve to the right. So we'll see that here, curve to the right. No matter which way you go, that high pressure air is going to tend to curve to the right. Now, this curving effect, the Coriolis force, is most evident over large distances and at higher elevations. So it's not enough then to just say that the air is moving away from a high and straight toward a low. And so what I'd like to do is show you a brief video that helps illustrate this with some good animations on the Coriolis effect.
So to explain the Coriolis effect, let's consider what would happen if the Earth did not spin. If the Earth did not spin, then air would want to move directly from a high to a low in a straight line. Okay? So any winds that we would have would be directly between highs and lows. But that's not what we observe on Earth. What we observe is that winds in the northern hemisphere are deflected to the right. So the wind's trying to move from high to low, but it can't ever get there because it's always being moved to the right and ends up going in a big circle around the high in a clockwise fashion in the northern hemisphere or counterclockwise in the southern hemisphere. So to try to explain this, I have one little demo here, and what we're looking at, so imagine this is the Earth and we're looking straight down the North Pole, right? So if I have wind that's moving from the North Pole to the equator, and the Earth did not spin, wind is trying to move in a straight line like this, right? Okay, but now let's imagine that the Earth is spinning, and the Earth spins counterclockwise on as you look from the perspective of the North Pole, right? So now, if I move my wind in a straight line, kind of clumsy, but what I see is that my wind, from the wind's perspective, is moving, it's making a big right-hand turn, right? It turned to the right. And that was simply due to the fact that the Earth is spinning. So I was trying to hold a straight line as I was turning that. So that's one demonstration of the Coriolis effect. I've got a couple videos here that I will also show you.
The Coriolis force is an apparent force that causes moving objects to appear to bend away from their intended paths. This force can be due to a rotating Earth, or in this example, a rotating platform. On a non-rotating platform, we can see that a thrown ball moves in a straight path to the receiver. Suppose the platform begins to rotate counterclockwise, just as the Earth rotates counterclockwise when viewed from above the North Pole. On the screen to the left, we see that the thrown ball moves in a straight line path. However, when we view the thrown ball on the rotating platform, the screen on the right, the camera reveals that because the platform is rotating, the ball in flight appears to curve to its right, and the receiver has to lean to the side in order to attempt to catch it. Even though the ball actually moves in a straight line, people sitting on the rotating platform see the ball appear to bend to the right of its intended path. The apparent bending of the thrown ball is due to the fact that the platform is rotating. The apparent force that causes the bending is the Coriolis force.
So this animation explains Coriolis effect in a little bit different way, and I think it's great, except the graphics aren't necessarily the highest resolution. But we start out, we've got 2 points that are on the same longitude but different latitudes. And so the point is that as the Earth rotates, these 2 points are going to rotate together, right? But if you look at the paths of each of these 2 parcels, they're going to be different. The parcel that was closer to the equator, the lower latitude, had to travel farther in the same amount of time, so it had to be moving faster. So now imagine that you've got a rocket at the equator and you're going to shoot it straight at this red dot, okay? But because the rocket is at a lower latitude, it has a higher easterly velocity, so it's moving to the east faster than this red dot is for the reasons we just saw. So if you shoot the rocket in a straight line, it appears that it turned to the right. But from the rocket's perspective, it was going in a straight line the whole time. It just had more easterly momentum than the red dot does, and it appears to curve off to the right. Then you can think of the opposite case. Now imagine the rocket is at the North Pole, and you're going to shoot it straight at this red dot, okay? But now the red dot at a lower latitude has a higher velocity to the east, and the rocket doesn't have any. So again, it misses, and from the perspective of the rocket, it's going in a straight line, but the perspective of someone on the ground looking at this, it looks like it went too far to the right. So no matter which way you go in the northern hemisphere, if you move it in a straight line, you're actually being deflected to the right from the perspective of the person on the ground. That's what the Coriolis effect is. And the Coriolis effect only works on something that's a very, very long distance. So there's a lot of folklore and urban legend about Coriolis effect. So a common one is that toilets flush clockwise in the northern hemisphere or counterclockwise in the southern hemisphere, or maybe it's opposite. Coriolis effect only affects things over a very, very, very long distance. So you can make a toilet flush either way in either hemisphere. It doesn't change it. If that was true, if the Coriolis effect was so strong that it would rotate water that only moved a few inches, it would basically be impossible for us to drive cars. We would just go flying off the road to the right, or even if you just started to run, it would be flying off to the right all the time. So it doesn't happen that way. It just works on things that are operating very long distances. So let's return now to our those 3 handouts that we were looking at earlier. So these, again, these sea level pressure maps. And so now what we can do is we can make predictions about the direction of the wind. So the first one we looked at, this is map number 1, high pressure, this big blob here. I know now that winds travel clockwise around a high. So I know that around this high, I'm going to have winds that are moving in a clockwise fashion. Now, In this class, what we're going to do is we're going to assume that the winds are traveling parallel to the contour lines. So in other words, I know the wind's going to be doing this. So I'm drawing lines that are parallel between these contours, but they're overall going in a clockwise fashion, right? So if I ask you, okay, what is the wind, well, let's say in Albuquerque, what's the wind in Albuquerque doing? Well, right here, if you drew an arrow, the wind is coming from the southeast and is traveling to the northwest. So here's a convention with wind. Wind is always described in the direction it's coming from. So if I have a north wind, that means it's coming from the north, right? If I have a westerly wind, it's coming from the west, okay? So we can predict which way the wind's going to be blowing by simply thinking about, okay, do I have clockwise or counterclockwise? And then drawing little short segments that are going clockwise, in this case around this high, but staying parallel to these contour lines. So let's...
Okay. So that was kind of a difficult subject to demonstrate, and so I appreciate Mr. Strong's assistance in helping us with those visual aids for the Coriolis force. One thing that I wanted to emphasize is that at the surface there is more resistance to the motion of the air. The air molecules encounter trees, different structures, and so this tends to change the flow pattern from what you would expect at higher elevation. And so this is the kind of flow pattern you would see near the surface. This would be a combination of the clockwise motion that we were talking about earlier, and also the tendency of the air to flow away from a high and toward a low. Okay? And so we see then that we have these curved paths, that they have a component of motion that's in the radial direction. So this is our near surface winds. Now similarly, for a low pressure region near the surface, it's going to tend to move in a counterclockwise direction at high elevation, but near the surface, it's going to tend to spiral inward toward a low pressure region, so that it has this sense of motion not only around this way in a counterclockwise direction, but also the motion inward that we would expect that a low pressure would have because of the fact that high pressure air tends to move toward lower pressure air. So near the surface we have a combination then of the fact that the air doesn't just move from high to low, it keeps missing because of the rotation of the Earth, but also the Coriolis forces. However, when you go to altitude, then the sense of the pressure lines is essentially the same as the direction of the winds. And so at high elevation, this is what you would see from a satellite. The wind velocities are parallel to the equal pressure lines. So let's redraw this and set ourselves up with a slightly different kind of a high and a low pressure situation. Let's say that we have a low on the East Coast in which the lines of constant pressure are fairly closely spaced. Then we have a high pressure on the west coast with spacing of the lines maybe slightly more expanded. So what I'm seeing here then is that the spacing between these lines is greater. That tells us that the pressure gradient is lower. Near the high, because the spacing of the lines is greater. Whereas here, in this particular example, we have a spacing of the equal pressure lines around the low pressure region are tighter. So this tells us that the wind velocities are higher. And we have a large pressure gradient. If you're at all familiar with topography maps, what you'll see are lines of equal elevation. And if they're very closely spaced, what that tells us is that you're essentially level. And so here, if we have lines that are more equally spaced, or if the lines are very far apart, like what would be the case here, maybe you have something like this, then in this region, there are very few lines at all, and so we would say that the pressure doesn't change. And we would imagine that the wind velocities would be proportionately low in a region like that. But here, what we would see is that around the high at elevation, we want the velocity of the wind to be parallel to our equal pressure lines. And so the velocity at each point then could be thought of as being a tangent to one of these equal pressure lines as we go around, but circulating in the counterclockwise direction. That's in the northern hemisphere. You go to the southern hemisphere, it would be circulating in the clockwise direction. Everything is reversed with the Coriolis force in the southern hemisphere, as we discussed earlier. And with a low pressure, you would want your lines to be parallel to the equal pressure lines, but circulating around in a here the high pressure we want to be going in a clockwise direction. Oops. And then the low pressure we want to be going in a counterclockwise direction. And then here's our counterclockwise around the low. Okay, so what happens then if we continue this pattern out to where the high pressure region meets the low pressure region? So in this area here we might have, say, 1013. That might be sea level. So in this area then we would have air moving down from above and probably fairly clear skies. Here we might have a storm, because we have very high wind velocities and we have a lot of instability. Very rapid changes in pressure could give rise to very unstable clouds, and it's possible that with the pressure lines so closely spaced that we could actually have a fairly nasty storm. So if we wanted to figure out what the wind velocities were at a point that was between the high pressure and the low pressure region, we would be doing counterclockwise around the low and clockwise around the high. But you can see that it doesn't matter. When you get to this point in between, those both match up to be a wind velocity that's in the same direction. And so just summarizing here, we would expect at high elevation, the motion of the wind would look like this, but here it would be faster around the low. Possibly very stormy weather here. If we looked at the surface features here, we would see the air moving away from the high, but curving to the right. So that it has this component of clockwise motion, but also near the surface we also have the motion which is away from high and close to low. And in this low pressure region, you would have the air curving toward the low. So the air has this component of motion that's moving inward this way, but while that's happening, you have the Coriolis force that is associated with the counterclockwise circulation about that low.